Welcome to the next part of this continuous function on metric space. Here is one theorem. If f and g are continuous functions from metric space m1 into metric space m2, then f plus g, f minus g, f dot g and f upon g are continuous on m1. Here for fourth property, this is the condition: g of x is non-zero where x belongs to m1. This theorem we can write by using Venn diagram. Suppose m1 and m2 are the two matrix spaces and f and g are the two functions, continuous functions. If f and g are continuous functions from this m1 to m2, then algebra, that is plus, minus, product, division, are also continuous between these two functions on m1. This is we want to prove. Now with these two definitions we can easily prove this theorem. What is first definition? Let M be a metric space and f and g are again two real valued functions which are continuous at a belongs to m. म्हणजे m हा एक मॅट्रिक स्पेस आहे आणि f आणि g हे दोन काय आहेत? फंक्शन्स आहेत, रियल वैल्यूड फंक्शन्स which are continuous at a belongs to m. Here is a and f and g are the two continuous functions. Okay. Then algebra is also continuous at a belongs to m. This is one definition. F and g are the real valued functions and which are continuous at a belongs to m. Now next that is m1 and m2 be two metric spaces and f from m1 to m2. This is the one function. m1 and m2 be two metric spaces and let f from m1 to m2 we say that function is continuous. When we say that function is continuous from m1 to m2, if it is continuous at every point, at each point, if it is continuous, if f is continuous at each point in m1, then and then only we say that function is continuous from m1 to m2. Means this is the definition of function is continuous from m1 to m2 when it is continuous at each point. Here both functions are real valued functions and we have to say that function is what? Continuous at a belongs to m1. Then algebra of that also continuous. This is we want to prove. What we want to prove? F and g are continuous functions from matrix m1 to m2 and algebra is continuous on m1. Therefore our intention should be here. What is this? Then we can understand the phenomena regarding this continuous function on metric space. Here we say that these functions, we have to show that functions are continuous on m1. Functions continuous on m1. Here definition says that functions are real valued functions which are continuous at a and algebra between them is also continuous at a belongs to m. And this is the third definition. Third statement. And therefore from these two statements we can say that all four properties, that is plus g, f minus g, f dot g and f upon g are true on m1. Yes, and hence we can say that algebra is continuous on m1. Means only in this proof of the theorem we consider these two statements and relate that we get proof of this theorem, because here this part is related to this and second part is related to this. If that function is continuous at each point of m1, then ultimately that function is continuous, and therefore we say that theorem is proved. Okay. Now some statements are important for MCQ. Therefore here we write any polynomial function f is continuous on R1. Any polynomial function is continuous on R1. Polynomial function a0, we know that p of x is equal to say a0 plus a1x plus a2x square. This is polynomial function plus an x raised to n, and this is a continuous on R1. Second, any constant function is a continuous on R1. Suppose f of x is equal to constant c, say, then c is constant, then this is also continuous function. Means any polynomial function is continuous on R1, any constant function is continuous on R1, and also in between them algebra means f plus g, sum, difference, product of such above functions are also continuous. Fourth is the one illustration regarding quotient. The function h defined by this 1 plus x cube upon 1 plus x square. What is 1 plus x cube? This is polynomial. What is 1 plus x square? This is again polynomial. Therefore, polynomial function is continuous function. This polynomial is also continuous function. And this structure is as like this, f upon g. F is continuous, g is continuous. Therefore, h of x is also continuous. And last, that is one statement regarding RD. What is that? We know that RD, discrete metric space. We have seen in the definition and examples on metric space. I think there is a second example of metric space which is of RD. D from R by R to 0 infinity, defined by d of x is equal to 0 if x belongs to R, and is equal to 1 if x y belongs to R and they are not equal. Then this type of metric space, you may say RD, or say RD is a metric space, but discrete metric space. Let f function from RD to m, means discrete metric space into metric space. For any a belongs to RD, for any b of a1 means open ball of radius 1 about a contains single element a, because a belongs to RD. Therefore, we can write it. And further, for epsilon greater than 0, from this we say that open ball of epsilon about f of a in codomain, f of a contains b of a1. That is, this statement in last lecture we have seen that this is the definition of continuous function, and hence function is continuous at a belongs to RD. What it means? If function is as like this from RD to m, for any a belongs to RD, that function is continuous on that a. That is, in short, this is every function from RD into metric space, means every function from RD into m is a continuous on RD. Is continuous on RD. This is the example about continuous function. In next part, let us see next article from this unit, open sets and then closed sets. Let us see on next time. Thank you.